Hello, everybody, and welcome to today's module on model training and optimization. I am Ibrahim Malik, and as an AWS certified solutions architect, certified AI practitioner, machine learning specialist, I am excited to guide you through this critical phase of machine learning lifecycle. In the next 10-15 minutes, we will explore how to effectively train machine learning models using AWS services. Whether you are just starting your journey in AI or looking to optimize your existing workflows, understanding these concepts will help you build more effective, scalable, and cost efficient machine learning solution. All right, so let's begin by understanding what makes model training on AWS so powerful and the key steps involved in the process. Okay, so introduction to model training on AWS, right? So AWS provides a comprehensive ecosystem for training machine learning models at any scale. At the center of this ecosystem is Amazon SageMaker, which is AWS fully managed service designed specifically for building, training, and deploying machine learning models. What makes SageMaker particularly valuable is that it eliminates much of the heavy lifting associated with each step of machine learning process. You don't need to provision or manage infrastructure, which means you can actually focus on more on the data science aspects rather than DevOps, right? So beyond SageMaker, AWS offers several other options for model training. EC2 instances with GPUs are excellent for compute-intensive deep learning workloads. The P3 and P4 instances, for example, provide access to NVIDIA Tesla GPUs that can significantly accelerate training time for complex models. AWS Batch allows you to run batch computing workloads, which is useful for distributed training across multiple machines, right? And for those existing TensorFlow or PyTorch workflows, AWS Deep Learning AMIs can come pre-configured with popular deep learning frameworks and tools, right? One of the key advantages of using AWS for model training is the ability to scale resources up or down based on your needs. So remember, we've been talking about how to conserve your capital or how to bootstrap your work, right? And with the AWS pay-as-you-go model, suits well. Right. So this elasticity of scaling up or down ensures that you pay only for what you use while having access to virtually unlimited computational power when needed, right? So before we dive into the training process itself, let's first discuss how to select the right model for. Excuse me. All right. So model selection, right? So selecting the appropriate model architecture is crucial first step in machine learning process. The right choice depends largely on the type of problem you're trying to solve. For classification problems where you're trying to categorize data into discrete classes, you have several options. Logistic regression is simple and interpretable, great for binary classification times. Decision trees and random forests work well when you need to understand feature importance, right? For complex patterns, neural networks can capture intricate relationships in your data. For regression problems, when you are predicting continuous values, linear regression serves as a straightforward baseline, right? XGBoost has become incredibly popular for tabular data and often performs exceptionally well in competitions. Neural networks can also be adapted for regression tasks, especially when dealing with large data sets. For clustering problems where you're trying to discover natural groupings in your data, K-means is a classic algorithm that works well when your clusters are roughly spherical. DB-scan is better when clusters have irregular shapes. So when choosing a model, right, always consider the trade-off between model complexity and interpretability. More complex models like deep neural networks might capture subtle patterns in your data, but they are often considered black boxes, right? Because it's difficult to understand how they arrive at specific predictions. On the other hand, simpler models like decision trees offer clear interpretability but may not perform as well as complex tasks. Your choice should be influenced by the size of your data set, available computational resources, and the requirements for the data deployment, right? So for instance, if you need real-time predictions, a simpler, faster model might be preferable, even if it sacrifices some accuracy. All right, now that we have discussed model selection, let's look at the actual training process, okay? The training process is where your model learns from data, and it involves several important steps. First, you need to first you need to define your model architecture, right? This includes specifying the number of layers in a neural network, the number of neurons in each layer, activation functions, and other structural elements. In SageMaker, you can build in algorithms or bring your own custom code. Second, it's critical to split your data appropriately. The training set is what your model learns from directly. The validation set helps you tune your model during training, and the test sets, which we'll use later, evaluates the final performance. A common split is 70% for training, 15% for validation, and 15% for testing. But this can vary based on your data set size and specific requirements. Next comes the actual training phase, where an optimizer adjusts your model's parameter to minimize the loss function. Popular optimizers include, SGD, stochastic gradient descent, which is the most basic approach, or ADAM, which adapts the learning rate and is often faster to coverage, or RMS prop, which works well for recurrent and neural networks. In SageMaker, training is handled by creating a training job. You specify your data sources, the algorithm to use, the instance types, and any hyperparameters. SageMaker then provisions the necessary resources, train your models, and saves the resulting model artifacts. So let me walk you through a typical workflow. Okay, so prepare your data in S3 bucket, configure your training job in SageMaker, launch the training job, monitor training matrix in real time, and once complete, SageMaker saves your model to S3. Throughout the training process, it is important to monitor for issues like overfitting, right? When your model performs well on training data but poorly on new data, right? Or underfitting, when your model fails to capture the underlying pattern. This is where proper validation comes in. Now, even with the best model architecture, your performance might still be suboptimal if you don't tune your hyperparameters correctly, right? So let's discuss that next, all right? How do you do hyperparameter optimization? So hyperparameters are settings that govern the training process itself, rather than the model parameters that are learned during training examples. Examples include like learning rate, batch size, number of hidden layers, regularization strength. The challenge is that there is no analytical way to find the optimal hyperparameters. They must be discovered through experimentation. This is where the hyperparameter tuning comes in, right? There are several approaches to hyperparameter optimization. We can do grid search. Systematically works through all possible combinations of predefined hyperparameter values. It's thorough but can be computationally expensive, okay? Random search randomly samples from the hyperparameter space and often finds good solutions more efficiently than grid search, especially when only a few hyperparameters significantly impact performance. Bayesian optimization takes a more intelligent approach by using past evaluations to inform which parameter combinations to try next. It's particularly useful when evaluations are expensive, okay? Amazon SageMaker provides automatic model tuning with which implements a Bayesian optimization approach. Here's how it works. You define the hyperparameters you want to tune and the ranges. You specify an objective metric to optimize such a validation accuracy. SageMaker launches optimal training jobs with different hyperparameter configurations. And then it intelligently explores the hyperparameters space based on previous results. And finally, it identifies the best performing configuration. What's powerful about SageMaker's approach is that it dramatically distributes the training jobs across multiple instances, possibly and potentially saving you hours or days compared to sequential tuning approaches. For example, if you're training a deep learning model, you might tune learning rate between 0.0001 and 0.1, batch size from 32 to 512, drop out rate from 0.1 to 0.5. So SageMaker would then run concurrent training jobs, each with different combination of these values to find the optimal set. Once you've trained and tuned your model, the next crucial step is evaluation, determining how well your model actually performs. So evaluate your ML models, right? Model evaluation is critical because it tells you how well your model will likely perform in the real world. Different types of problems requires different evaluation metrics. For classification problems, accuracy measures proportion of correct predictions, but it can be misleading for imbalanced data. Precision tells us what proportion of positive identifications was actually correct. Recall or sensitivity tells you what proportion of actual positives was identified correctly. F1 score is the harmonic mean of precision and recall, providing a single metric that balances both. Okay. So for regression problems, root mean square error or RMSE measures the standard deviation of the prediction errors, right? Mean absolute error, MAE, is the average of the absolute differences between predictions and actual observations. And R squared indicates the proportion of variance in the dependent variable that's predictable from the independent variables. And for binary classification, the AUC-ROC curve, area under the receiver operating characteristic curve, is particularly useful. It measures a model's ability to distinguish between classes and is insensitive to class imbalance. So in SageMaker, you can easily calculate these metrics using built-in functionality. So deploy your model to a SageMaker endpoint, right? Use the endpoint to generate predictions for your test data, and then compare the prediction to the ground truth and calculate the relevant matrix. Alternatively, you can use SageMaker processing feature to run evaluation code as a separate job. Remember that the best metric depends on your specific use case. So for a fraud detection system, recall might be more important than precision because the cost of missing a fraudulent transaction or false negative is higher than the cost of investigating a legitimate transaction, false positive, right? So let's wrap it up, right? Key concepts, key best practices. Number one is start with simple and establish a baseline before moving to more complex models. Use cross-validation to ensure your model generalizes well to unseen data. Monitor both training and validation metrics to detect overfitting early. And document your experiments, including hyperparameters and results, so you can track your progress. And consider the computational cost. Sometimes a slightly less accurate model is preferable if it is slightly faster to train or deploy. And for deep learning, leverage transfer learning when possible to benefit from pre-trained models. Use SageMaker's managed spot training to reduce costs for non-time sensitive workloads. So AWS provides a robust ecosystem for model training and optimization, and SageMaker streamlines many of the complex tasks involved in this process. By understanding the concepts we have covered today, you're well equipped to build more effective machine learning models. In our next module, we will discuss model deployment and how to make your trained models available for inference. Until then, thank you for your attention, and I look forward to continuing this journey with you.